day, dear viewers and listeners. You are welcome to another edition of our weekly online chemistry class. In the previous episode or season, we started isomerism. And I told you that isomerism can actually be classified into two. We have the constitutional and the configurational. The constitutional, we have structural isomerism to be precise, while under the constitutional, we have the conformational isomerism as well as stereoisomerism, which we have been able to do justice on. But on stereoisomerism, we were able to discuss geometrical isomerism. And today, this episode will strictly be on enantiomerism, which is the other type of stereoisomerism under constitutional isomerism, configurational isomerism that we have. But before we proceed, do not forget to subscribe to our YouTube page for more videos. Enantiomerism. Enantiomerism can be defined as a phenomenon whereby an organic molecule exists in two or more stereoisomers that are not superimposable mirror images of each other. That is, when such molecule is placed in a plane of polarized light, the molecule can rotate in either direction. So when it rotates to a particular direction, the image of that molecule will also rotate in another direction. So such molecules that have ability to rotate in the plane of polarized light is referred to as an optical isomer or enantiomer, while the phenomenon is known as optical isomerism or enantiomerism. Now, for a molecule to be optically active, such molecule must possess a characteristic that we refer to as chirality. Chirality is obtained from the Greek word ke, which means hand. And we are coming to that. Now, when will a molecule be chiral? For an organic molecule to, or for a molecule to be chiral, the molecule must possess a carbon atom that contains 4 different atoms or group of atoms attached to it in that molecule. For instance, if you have this carbon atom, you have a substituent P, another group Y, another group X, and another group Z. If all these groups are not the same, then we say this atom is a chiral carbon. We refer to it as chiral carbon or chiral center. You can also call it an asymmetric carbon or asymmetric center. You can also refer to it as a stereogenic carbon or a stereogenic center. It is asymmetric in nature because you cannot divide it into 2 equal halves. So when you place this molecule in a plane of polarized light, the molecule will rotate in certain direction. And the direction of rotation is a characteristic of that molecule. Now, let's do a little experiment. If you are able to, if you place your right hand in front of a mirror, what is going to appear will look exactly like your left hand. You can try that. That means your hand is optically active. Being optically active means it is it exhibits what we call enantiomerism. That means you cannot, both your left and your right hand are not superimposed on each other. Meaning there is no way you can, pardon my manners, there is no way you can place your right hand on your left hand that the two or all the fingers will cancel out one another. If this is well aligned, then your thumb here will be on the smallest finger of the left hand. So that means they are mirror images and they are not superimposable on each other. And that's exactly, there are some organic molecules that possess that characteristic. Meaning, if you place this in front, in a plane of polarized light, okay, you are going to have something of this nature. This Z will be here, then you have your X, your Y will be here, and you have your P. So this is the image of this. And these two are called enantiomers or optical isomer. So when this rotates in the direction of rotation of this will be the opposite of this. And that is what we mean by, in fact, enantiomerism or enantiomer is also obtained from the Greek word enantiom, which means opposite. Now, before we understand the chemistry of enantiomerism proper, we need to, there is a way of displaying the structure of an organic compound. And two formulae are usually inclined. And those are, we have the perspective formula and we have the Fischer projection formula. Now, in the perspective formula, the molecule can be represented in this manner. So you have the chiral center, you have a bond here, then you have another bond here. There is you have a solid wedge, then you have another bond here. You may have another bond here or a ash wedge. The ash wedge is normally represented like this. Then you have another bond. So if this is element P, this is a substituent Z, this is X, this is Y. We have something of this nature. So that means this solid wedge is the bond that is protruding that is on a two-dimensional plane that we normally have in a sheet of paper. If it is three-dimensional plane, this is very easy to understand. But let's take an example. The other formula is what we refer to as Fischer projection formula. The chiral center is indicated as where all the substituents join the particular carbon here. So this is the chiral center. You have the P, you have the Z, you have the Y, then you have the X. This is Fischer projection formula, while this is a perspective formula. I want to take you through, you should understand that not all organic molecules can exhibit isomerism. As I said, for a molecule to exhibit isomerism, all the groups that are attached to that particular carbon must not be the same. For instance, if this Z is Y, then this molecule is not optically active because you can divide it into two equal halves. So there are different parts of our body that are optically active. Take note of your air as well as your food. So let's look at 2-chlorobutanol. 2-chlorobutane. 2-chlorobutane is CH3, CH, Cl, CH2, CH3. Of course, this molecule has a chiral carbon, and that is carbon 2. On carbon 2, you have 4 different groups attached to it. There is a methyl group, there is a hydrogen atom, there is a chlorine atom, as well as an ethyl group. Now, if you want to represent it in either of the formulae, whether perspective or Fischer projection, you can, first of all, if it is perspective, locate the chiral center, which is carbon 2. Now, draw out all the 4 bonds. You have something like this, you have something like this. Then we have the ash, and we have the solid wedge. Now, you can arrange the groups in any form. You can choose anyone to attach here, put anyone here, in any way or any form you want. So that means here we can put chlorine here, we can put ethyl group here, we can put hydrogen here, and we can put methyl group here. Now, when you place this compound in front of a mirror or a plain polarized light, you are going to have the mirror image, which will be something of this nature. So you have CH3 here, then you have the hydrogen here, you have the chloro as well as the ethyl group. Now, there is what we call, to distinguish these stereoisomers or the enantiomers, because enantiomers usually have the same properties in a chiral medium. They have the same similar boiling point, similar melting point, at times the same chemical reaction. But what differentiates them is the configuration and their direction of rotation in a plane of polarized light. Now we need to determine the configuration of each of these molecules, which are enantiomers. Now, to determine the configuration, we use what we call the CaninGold pre-log system. And as we use it under geometrical isomerism, for the E and Z, cis and trans geometrical isomerism. Now, the rules remain the same, meaning you have to rank the substituent based on their atomic number. And the substituent with the highest atomic number will be ranked first, while the substituent with the lowest atomic number will be ranked lowest. So here, what is directly attached to this chiral center is chloro. Here you have hydrogen, here you have carbon, and here you have carbon. Then this carbon is attached to 2 hydrogen atoms. So meaning chloro has atomic number 17, hydrogen 1, carbon 12, carbon 12. So this chloro group is ranked first, followed by ethyl, because ethyl is bulky, is more bulky than methyl. So you have this as 2, this as 3, and this as 4. So that means you are now going to draw a cycle, an arrow from the highest ranked substituent to the second highest ranked substituent in that direction. So the direction of rotation, of the arrow, when the arrow is pointing anti-clockwise, that means the configuration of the molecule is S. We refer to it as sinister. Sinister means anti-clockwise or left. Okay, now the same thing here. We have 1, 2, 3, 4. You can see when you draw an arrow from the highest to the second highest and so on, this one is in the clockwise direction, rotating or moving towards the right. So that means this is R configuration, which is known as rectus, which means to the right. Now, the same thing applicable to when you have Fisher projection formula. If we draw the Fisher projection formula of the molecule, similar expression is this. You have this is the chiral carbon. You have chlorine here. You have an ethyl group here. You have methyl group here, and you have hydrogen here. So here, this is 1, 2, 3, 4. And of course, you can see that the direction of rotation of this molecule, based on the configuration and the CaninGold pre-law system, is also anti-clockwise, which is the configuration of the molecule. That is X. However, there is a reservation here. Whether perspective formula or Fisher projection formula, you have to be very careful. When you are using the perspective formula for the structure of the molecule, the lowest ranked group attached to the chiral center must be on the ash wedge. But if it is not on the ash wedge, then you have to interchange 2 groups so that the lowest ranked molecule will be on the ash wedge. Let's take an instance. Look at this. You have something of this nature, COOH. Here you have CH3. Then here you have, okay, assuming there is hydrogen here, you have CH3 here, and you have OH here on the ash wedge. OH. If we are ranking this molecule, this will be ranked first, followed by this, because this carbon, but attached to this carbon is hydrogen. You have to go to the next element. The next atom that is attached to the atom that is directly attaching to the chiral center. So we are after this carbon is oxygen, after this carbon is hydrogen, and oxygen is more of higher atomic number than hydrogen. So that is why this is 2, this is 3, and this is 4. So in that case, you have to you can see that the 4th rank group is not on the ash wedge. If it's on the solid wedge or on any other bond, you have to make sure it is on the ash wedge. So if we rotate, if we look at the configuration of this molecule from the first to the second, you move towards the highest rank towards the second highest rank, not that you come from the highest to the third. So it has to be in this direction. You can see that we are going to omit the 4th rank group, the lowest rank group, before we get to the 3rd. So we can say this molecule is sinister, that is anti-clockwise. But to get the actual structure of the molecule, because the lowest rank is not on the ash wedge, you have to interchange the group 1 and group 4. Move the one that is on the ash wedge to where the lowest rank is and change the lowest rank to that particular spot. So you are going to have something of this nature. You have carbon, COOH, OH, CH3, and you have hydrogen. So you are now going to tell us the order of configuration, where this is 1, 2, 3, 4. From here, you can see that this is clockwise. That means this molecule you have here is the enantiomer to this, because this is the actual way the molecule was before you interchange. So the configuration of the molecule before switching one or two groups is R. After switching groups is R, as you can see, clockwise. But before you switch it, it was S. So that means, so when you have a case like this, the configuration of the switch molecule is the opposite of the configuration of the actual molecule. So since the switch molecule is R, that means the actual molecule has S configuration. So the molecule is S. The same thing applicable to this. In Fischer projection, the lowest rank group must be on vertical bonds, not horizontal. If it is horizontal, then you have to switch as you did here, and the configuration of the switch enantiomer is the opposite of the configuration of. So look at this. This is horizontal. The lowest rank here is horizontal. So, and if we look at that, it was 1, 2, 3, 4. That is anti-clockwise. This was S. But if we switch this, probably we move this here, so that we now have methyl group here. Let's assume hydrogen here and methyl group here. What do we have? 1, 2. This is 3, and this is 1. So 1, 2. This is anti-clockwise. That means the configuration of the actual molecule must be clockwise, which is R, if this is S. So that is what we mean by optical and how to determine the configuration of enantiomers when placed in a plane of polarized light. So you have to be careful. When you are given the molecular formula of a compound, write the structural formula of that compound. Then try to locate if the molecule has a chiral carbon, a carbon that is being surrounded with 4 different groups or group of atoms. When you have such, you can say that particular molecule is optically active and because it can rotate in a plane of polarized light. Then what do we mean by optical activity? Optical activity. Optical activity is the activity of the molecule. That is, when you place a molecule that is chiral in a plane of polarized light, the molecule rotates in certain degrees, and that degrees of rotation can be determined using what we call a polarimeter. A polarimeter. Now, we have observed rotation. The observed rotation is usually observed when you place that particular molecule in a plane of polarized light. Okay? And when you place a molecule in a plane of polarized light, the molecule can rotate in either of 2 directions. There are 2 directions of rotation. The first is to the right, which is clockwise, and the other is to the left. So when a molecule rotates in a plane of polarized light, rotate towards the right direction, we call it dextro-rotatory. And that is indicated as plus. But when the molecule rotates to the left, we call it levo-rotatory. And that is indicated as negative or minus. Please do not mistake this this sign to the configuration R and S. Plus never means R, while minus never means S. The R and S indicate the configuration, how the groups that are attached to the chiral center are being arranged. While the plus and minus represent, they can also be represented as D or M, represent the direction of rotation of that enantiomer when placed in a plane of polarized light. Now there is also what we call specific rotation, and that specific rotation is normally used to distinguish between 2 enantiomers. A better way of distinguishing them than the observed rotation. Now the specific rotation is dependent on the concentration of that particular enantiomer in the solution. The concentration is measured in gram per milliliter, and it is also dependent on the path length of the sample tube, and that is represented as small letter L, measured in decimeter, and also dependent on the wavelength as well as the temperature of the system. So that means when the concentration of the solution is double, of course, you expect a larger degree of rotation of the molecule in terms of specific rotation. So that means we can represent this as an equation that the specific rotation at a particular temperature and wavelength is equal to the observed rotation divided by the path length times the concentration in gram. So this alpha indicates the observed rotation. This alpha in parentheses indicate the specific rotation of the molecule at a particular temperature and wavelength. Let's take an instance. Assuming you have a molecule that is having a mass of 1.5 gram placed in a solution of 15 centimeter. You can see that. And in a sample tube with path length of 10, a solution of 15 milliliter. Okay, a sample solution, a path length of the tube of 10 centimeter. Okay, at a particular temperature and wavelength. So, what is the observed specific rotation? If the observed rotation is plus 1.6 degrees, that's the observed rotation. We are looking for the specific rotation. So that means our specific rotation at that temperature and wavelength is equal to observed rotation over length times concentration. You might be given a specific rotation and asked to look for observed rotation, provided all other parameters are known. So if you substitute, you have plus 1.6 divided by, the concentration of the solution is equal to the mass 1.5 divided by 15, which is the volume, and that will give you 0.1 gram per mil. Is 0.1 gram per mil. Okay, so we have the length to be 10 centimeter, and that same thing as 1 decimeter, because 10 centimeter make 1 decimeter, and your length must be in decimeter, not centimeter. Why the concentration must be in gram per mil, not mole per mil. So here we have the length, which is 1, times the concentration is 0.1. So that means the specific rotation of the molecule is plus 16 degrees. So that is the way of differentiating such molecule. Thank you very much. In our next episode, we are going to look at what we mean by optical purity and enantiomeric excess, as well as some important terms in, that we need to know under enantiomerism. Thanks for watching. See you again.